We're going to be starting our second session, which is on physical emulators. For those of you who are new to this topic, physics emulators are machine learning models that reproduce the output of physics-based climate science models at significantly lower costs. We're going to start with two invited keynotes from Yossi Matias and Muhammad Kasim. Our first keynote from Yossi is from Yossi Matias, who is the Vice President of Engineering at Google and the head of the Google R&D Center in Israel, which he established. He's now leading efforts in AI and search, including, most relevant to us, crisis response with SOS alerts, public alerts, and flood forecasting. He was a recipient of the 2005 ACM Gödel Prize for the profound impact of theory and practice of the analysis of data streams, and was elected in 2009 as an ACM Fellow. As a quick note, for those of you who have just joined, at the end of this talk, time permitting, we'll take questions from the Zoom chat. Those of you who are at iClear can also ask questions in Rocket Chat. Yossi, are you ready?
Hello. Hi.
That's how I feel about Zoom all the time.
Yeah, that's quite a different experience. Let's see. Okay. We try to. Typically, I use different technology for presentations, so always a first.
There should be a green share button at the bottom of the screen, right?
We're almost there.
All right.
Let's see. All right. Can you see my presentation? Can you see my presentation?
Yes, we can.
Looks good.
Yes, we can see it. Sorry for that.
Okay, great. So thanks for inviting me, and really pleasure to be here. And thanks for the audience. Pretty unusual kind of conference, but I'm sure we're all adapting. And first and foremost, I hope that everybody on this call are all well and healthy, as well as their families. Now, the topic of this workshop is really close to heart because it touches on several aspects that are, I find, extremely important. It's about how to use technology to address societal problems, and in particular, things related to climate change and sustainability, and more generally to social good. And indeed, I've been quite involved in the past few years on leading social good efforts, and in particular, AI for social good at Google. We're looking into how to leverage technology and AI in particular to address societal problems, both within the company as well as how to facilitate work outside of the company. So for example, just recently we concluded an AI Impact Challenge where we invited startups from around the world to address various topics around AI for social good in all areas of AI for social good. And just last week, we kicked off an initiative called Google for Startup Accelerator for sustainability development goals, where we had 11 startups selected out of 1,200 in Europe, Middle East, and Africa to address sustainable development goals. Now, today I'm going to focus on a particular problem, which is flood forecasting. And just to give a little bit of background, let me start with the more general problem of crisis responses. And as pointed out, I'm leading an effort at Google on crisis response, where typically it's about what we're focusing on is essentially how to address people's need for information during crisis. What we see here are the trends, the volume of queries that people are having during crisis. We can see the huge peak that we have during Chennai floods or Superstorm Sandy, Paris attacks. So it doesn't matter which crisis we're talking about. We see people coming to Google to look for information, to actionable information, which is how to remain safe. And typically they're interested in questions such as what's going on, where is it, what should they be doing? What kind of information should they know about it? So to that end, we launched just a few years ago, a feature within Search called SOS Alert, which essentially tries to address these kind of questions, which is to provide a kind of fresh information from news, on a map, and some relevant links and whatever is possible. And you might have seen a version of that which was launched recently for the COVID-19 epidemic, where we're actually launched for the first time an SOS Alert for a kind of a public health situation, where we're tried to use the infrastructure to provide answer and then evolved it into a much more richer experience in search. And indeed, just in the last, and what we're typically providing is information through search, through maps, and notification in Android for those in the vicinity of the event in what we call SOS alerts or public alerts. And just in the last 3 years, we actually had quite a few emergencies. These are large-scale crises for which we provided SOS alerts or public alerts, and we had over 2 billion views on those, not including the COVID-19. And again, these are all sorts of crises, anything from wildfire to other natural disasters and terror attacks, etc. In the process, we also learned that with really the infrastructure we have is providing, its aim is provide the information to people when available and as fast and as efficiently as possible. However, we discovered that is one of the most devastating natural disaster is our floods. And the problem with floods is that we just don't have the right information, because the most important information for people to know during floods is really the fact that it's about to happen, so that they can actually remain safe. So obviously there are many other needs, such as providing the right information after the fact to first responders to help them be more effective. However, the most important aspect of information that people really need is about prediction, about forecasting. Flood is about to happen. And this problem is difficult because obviously, and many people have been looking into that. So for the past 3 years, we actually set up an initiative on that. And just to highlight the significance of that, this is an example, a village called Narwar in the Bihar area in India. We were there in a group kind of to learn more about what's going on the ground. And what we see here are the remains, the only few buildings that remained kind of standing after a devastating flood that was there just a couple of days earlier. And the flood itself is actually kind of came through the night in a way that was quite unexpected. So, what we see here are actually the flood in that village. The video was taken during the day. The flood actually started during the night. And as you can see, this is pretty severe. In fact, 2 people lost their lives, and many more would have lost their lives if not for this fellow who personally saved quite a few by just taking them one by one. And what we see behind us, I'm standing near this fellow and Sela, who is leading the flood forecasting project. And behind us are actually the stranded families. They are actually in a shelter. Their village is totally lost. So this is one example. However, this is not a singular example. There are many people impacted over the world by floods. There's estimated 6,000 fatalities per year, 250 million people impacted, billions of economic cost. And of course, not everything can be avoided. However, we have enough studies showing that with the right, if we have some prediction of floods coming people's direction, with high confidence, then we could actually save lives and also some of the property, because some of the property can be saved if we know, say, a few hours or a couple of days before that the flood is arriving. And and indeed, what now we're expecting that with climate change, actually this problem is going to be even stronger, right? We're going to see more floods caused by the changes, by global warming and other factors. So we actually set up this effort to look into whether we can do anything about it. And one of the interesting aspects is that 3 years ago, we weren't very optimistic. The problem is difficult. People were looking into that. And here I should note, the problem is not about getting a reasonable prediction that something is happening. In many cases, we know that there's some big rains, significant rains coming, and there may be floods. In order to be effective, we really need to be to have very accurate predictions, because people are not going to take actions if we don't have high confidence on alerts. The cost of taking action is pretty high. And governments and responders can also not take actions on low confidence alerts because there are too many of them. And then again, the cost of that is too high. So really the challenge is to get predictions which are, say, 90% accurate, so that when you get an alert, you know you need to take an action. And when we have predictions of floods, authorities know that they need to actually to make the investment in order to address those. And the way the flood forecasting work is going is that it's essentially based on hydrologic models, on inundation models, and then we're using our infrastructure to send out the alerts whenever applicable. And again, the difficulty is to get all the information in place and to the right computation and see that everything is working. And obviously there are many parameters out there, because the soil is maybe different, the lay of the land may be different than what you know, and in order to get real-time computation, you need the very good data. And indeed, the hydraulic model is impacted by many of these kind of parameters. And what we've been doing is essentially making some progress on that by taking satellite imagery, using some data elevation model generation, which is highly accurate, order magnitude accurate than we had before, which is quite important, of course. And then in parallel with partnerships with governments, getting the real-time information from the ground and then putting it all together, and then using deep neural networks computation on using for simulations combined with physical hydraulic simulations of fluids, in order to make predictions of where the floods is. And in order to facilitate it, we're actually making a lot of calibration by running thousands of simulations on these particular areas, so that we can actually make corrections towards all these variables that I mentioned earlier. And even with that, it's not always clear what can be done. And what we discovered is that by putting all these together and through a partnership with the Indian governments, getting this gauge measure information, and using all these cloud computation and simulations and physical simulations and machine learning models, we can actually generate predictions which are accurate up to 90% confidence. So quite interestingly, we're having some of the measurements done the old way by people. In fact, in India, there's a very effective system which is based on people getting into the river on a boat with sometime with a stick, or reading out of a stick, and using some machinery in order to measure the depth of the water and the velocity of the water, writing it down on a piece of paper, going back to the office, making a call to the back office. All this information is getting into a system that then puts it as input, and combined with the most advanced machine learning models, it actually produces predictions. Obviously, we're also looking into ways in order to see whether we can use technology to modernize some of those readings. But the system is actually working well there. More important about this technique is to address areas that currently are not covered well by current operations. So this is one example. And in fact, when we're doing a tour in Bihar, we were looking very carefully into, there were ongoing floods there. So we're looking into our predictions, comparing them to situations on the ground to try and understand what are the reasons for the discrepancies whenever they're applicable. As I mentioned, there are 90% accuracy. So in those areas that were not accurate, we were very keen to understand what's going on there. And this is an ongoing work on that. Now, once we have the kind of predictions, then it's about getting it to the public. This is an example for one of our early alerts that we provided in a Goalpara area, where what you see here is a map providing kind of the three colors represent areas that we have 90% confidence there's a flood, and then the other reddish shows area that is covers with 90% recall of the area that is there with low confidence. So we'll try to both provide the high confidence area as well as the high coverage. And what we started just in the couple of years ago in Patna in one pilot is now kind of expanded along the Ganges and Brahmaputra. And last monsoon season, we already sent out over 1 million notifications to people at risk along the Ganges and Brahmaputra for floods in that area. And and the teams are working hard to further expand that. Now, interestingly enough, when we think about these early warning systems, there have been the World Bank looked into a survey into benefits and cost of illustrative investments and adaptations. And indeed, when you look at the first row, the strengthening early warning systems, even though its impact is in terms of net benefit is not the biggest one of all, its benefit cost ratio is really the highest. It's 9-to-1. And in a way, what we're tackling is that, and when you think about as it relates to the benefits on people's lives, then this could be quite significant because people getting these alerts in time can actually be safer taking action on that. However, in this context of adaptation, it's quite interesting to also watch into the second line, which is the biggest net benefits. What we see is 4 trillion on making new infrastructure resilient. And this touches on the opportunities, some of the opportunities around what we can do with the flood forecasting. So when we think about looking forward, obviously there's a lot of work ahead of us in expanding the flood forecasting. And I should mention that what we're currently focusing on the forecasting are what we call riverine floods. These are floods that occur due to rivers going over banks and where, for example, this is not covering flash floods and the like. There's a lot that can be done. So I'm going to mention 3 topics that could be quite significant in terms of adaptations. One is about scenario planning. The second one is infrastructure planning. And the third one is operational management. And in each of them, it turns out that the basic technology we're using for flood forecasting, which are hydraulic modeling, inundation modelings, are quite significant. In fact, in many cases, these are the core technologies that can allow us many other topics of adaptation. So for example, in scenario planning, in order to really understand what can be done, what should be done, what we really want to do is to run those simulations and think about replacing those measurements with various scenarios that we may be caring about. And this scenario planning is quite significant because then these can help us understand, for example, when making planning on where to invest in terms of more housing and otherwise, what are the potential risks down the line in all sorts of cases of based on probabilistic models of where we're going to have more rains and the other scenarios out there. Another one is infrastructure planning. In fact, that village that I pointed out earlier, the place I was standing on and we were standing on as a group viewing that was actually kind of the bank of a river that was stopping the water for many years, except that the water kind of went across because the level went too high. And this has to do with the question of where do you want to invest, because investment in infrastructure is hugely important, but also hugely expensive. So the question of how to make decisions about what kind of investment to do, where should one make strengthen the infrastructure in order to prevent floods, or where should one build dams in order to eliminate the risk or to reduce the risk. There are many considerations out there. And in order to do that, one needs to understand the implication of what happens, for example, if a particular, if there's a deformation of the land, which villages are going to be impacted or which cities are going to be impacted in various places. And when you think about long-term planning, say, that you'd like to do in terms of investment, then having the right hydraulic modeling where one can look in what-if scenarios is becoming quite important. Obviously, one of the important aspects here is the right partnership with the government, with authorities, and also building up the right kind of tools and technologies around the engine. But the core engine is, a lot of it is really about the hydraulic modeling and other components that we currently already have in the work. And last but not least is operational management. Now, tragically, some of the floods that we've seen and witnessed, including with fatalities, were actually caused by some operational decisions out there. So by water, at some point, in many cases, one need to discharge water for dams. And once a water discharge, there are going to be implications downstream. And to understand those implications is hugely important. For example, by understanding that by discharging water, there are going to be floods in certain villages, one can take decisions about scheduling of those discharges, on the magnitude of these discharges, and also about notifications, because if we know that we're going to discharge water that put at risk certain areas downstreams, then there's an opportunity here to actually do a better calculation. And again, it's not about a general warning that, hey, there may be water coming that way. As mentioned earlier, what's really important in order to be effective is to provide warnings which are very high confidence and very high probability. So it needs to be something like, in this particular area, there's 90% probability that we're going to have water in 2 days from now or in 6 hours from now. Now, by working together with governments and authorities, by putting the tools, the infrastructure tools together, and then by leveraging on the basic engines that I mentioned earlier, then there's an opportunity here to actually influence operational management considerations and make them more effective. So these are kind of a few highlights in a very high level. I would also note that there was a paper on some of the hydraulic modeling presented just a couple days ago in a workshop on earth sciences, if you care to learn more into that. And in conclusions, flood modeling is a critical component, climate adaptation, and there's going to be large impact, high cost effectiveness of doing that. There's much left to be done to prepare, especially addressing longer term risks, especially in low income areas. And there are good solutions require deep collaboration and between both the scientific community, research community, companies, and governments and organizations. There's a lot of challenge in such collaborations. I think there's a huge opportunity as well. And we're very optimistic. We're very encouraged by the kind of collaborations we've seen so far to date. And last but not least, since this is a scientific conference, there's a huge, significant opportunity for collaboration among research groups. In fact, we've been hosting a couple of workshops that we coined Machine Learning Meets Flood Forecasting, where we brought together many researchers from around the world to discuss and to the various techniques. As I mentioned, we are only touching here some of the areas of flood forecasting. There are many other areas that require attention, and there are many other techniques that can actually be shared, and ideas, either through collaboration, through inspiration, through knowledge sharing. And we've been also discussing ways in which we can actually make some of the technologies more shareable, some of the information that can be used in order to do this modeling and prediction, and many conversations going on in this direction. So with that, thank you very much for your attention here. There's going to be a breakout session later. Unfortunately, I won't be able to participate, but Sela, who's leading the project, I believe is going to be there. And thank you very much.
Thank you very much, Yossi. I've got time for about one quick question here, and I'm going to pull this from Joy Montiero in the audience, who asks if your flood forecasting initiative uses traditional hydrological models as well, and if so, what value add comes from the machine learning model?
Yeah, excellent question.
No, go ahead.
Yeah, obviously there's this can be a talk on its own, but I will just mention that, and again, I encourage to look into the talk that was given on Sunday in the Earth Science workshop, and also in the breakout session, perhaps Sela can elaborate more on that. But very briefly, we are using also hydraulic modeling techniques. Machine learning, so I think it's the idea is that we can have machine learning as a combination with hydraulic modeling. There are areas where not all the parameters are known. So for example, if you'd like to compensate for information that in order to calibrate for a particular area, we need to take historical data about floods in those areas and look into what can be done there and how to do the adaptations. There are some very interesting research work, by the way, also about how to accelerate physical modeling computations using machine learning, which I encourage people to take a look at. So I would say that it's a combination of both using machine learning in some areas instead of hydraulic modeling or physical modeling. In other areas, it's really enhance the computation with information that may be missing. And in other areas, it's about how to accelerate the computation. And there are very interesting techniques of doing that as well. We can't hear you, Kelly. I think you're muted.
Oh, thanks. So I was going to say, I would love to hear more, and I know that so would a few other people asking questions in the chat, but I'm going to have to move on to the next talk for the moment.
Thank you very much,
Thank you very
everybody.
much.
And looking forward to hearing from others as well.
Yep. And for those of you who were interested in what Yossi said about the previous talk at the AI for Earth Sciences workshop, the link to that is higher up in the chat. And we should have a recording of the talk by Zach Moshe talking about Google's flood initiative. All right. So our next talk is going to be by Mohammed Firmansyah Kasim, who is a postdoctoral researcher at the Department of Physics in the University of Oxford. He works on applying advanced computational techniques to solve problems in physics. Mohammed, are you here? All
Sorry,
right.
I was muted. Yeah, I'm here.
And as a last comment, to get us back on schedule, we'll take 5 minutes out of the breakout room discussions. Okay. So you have until 55 past.
Okay, 55 past. All right, cool. Thank you very much for the invitation. It's an honor to me to be invited for climate change workshop because I work in plasma physics, but no plasma physics seminar has invited me. Okay, so this is the work that I've been working on since the last 6 months on accelerating physics simulations using deep neural network. So, sorry. So this is the collaboration from 4 institutions, mostly from Oxford, and there are also university from Spain and USA. And we are all interdisciplinary research collaboration from physics, atmospheric physics, earth science, and fusion science. We are all working together in making this happen. So the initial motivation why we are working on this, because we've been working with computer simulations all the time in all kinds of research, mostly in physics. For example, if you want to understand like molecular properties, we run simulations, DFT simulations. If you want to design the batteries, we rely some of our work also on simulations. We want to understand the universe, we run simulations. And we want to design fusion reactors, we run simulations. So simulations is almost everywhere in physical research. But unfortunately, most of the interesting simulations are very hard to work with, mostly because they are very expensive and they're very slow. So for example, in one of the simulation in this work is the black carbon simulation using GCM model. And one simulation running one set of parameters to get 12 months profile of opacity in the atmosphere, it could take us about 1,000 core hours. It's just one simulation, so it has to run on supercomputer. That's only the forward simulation. And if you want to do like inverse simulation, for example, we know the observation and we want to know what the parameters are, we need to run hundreds or thousands simulation, which is practically impossible because one simulation could take 1,000 core hours. So this is the initial, so this is our motivation. We need something to speed up the simulation so that we can run it multiple times without draining our time and resources. So there has been quite a lot of research on building physics emulator. And these are just 2 examples that I could take, that I took from computational chemistry and atmospheric physics and astrophysics. So in computational chemistry, they have been building emulator to calculate the energy, and then they can simulate the molecular dynamics. using the emulator. So instead of running expensive DFT simulation, they just run the machine learning, which can be sped up to like 1,000 times. And then there's also cosmological simulation, which they call it Cosmic EMU. This has been around, I think, for 7 years now. It's quite popular in astrophysics. So challenge in building emulators mostly is that the emulators needs to be accurate, because it doesn't matter how fast your emulator is. If it gives you wrong answer, then the emulator is just nothing. It's not useful anymore. And also the most useful simulation to build emulator is slow simulations, where you cannot generate like hundreds of thousands or probably millions of data sets to train your machine learning model. So it is fairly limited for maybe like hundreds, or for relatively cheaper simulation, you can do like thousands or tens of thousands simulations. And if only a few data sets are available, this is the challenge, because overfit is really easy to get. So we need to get a high accuracy without being overfitting. So the idea is, we tried quite a lot of combinations of deep neural network, and by the end of the time, we end up with this kind of algorithm and architecture. We use the deep neural architecture search to find the best architecture. It's not best, to find a good architecture and train the weights simultaneously to match the predictions of the output of the simulations. So the simulations that we consider here are all simulation that takes n scalar inputs and then outputs one-dimensional signal, 2D or 3D signal. It doesn't matter, but the input is n scalar values. So we start by having a very big super architecture with a lot of option of convolutional operators in that, with some skip connection. If you can see the blue arrow here, they are the skip connections, and the groups of arrows are multiple convolutional operator that will be chosen one at a time. So to train this, we perform 2 steps update. So in the first step, we choose one operator for each group, and then do feed forward, calculate the loss, and then back propagate the gradient towards the operator that was chosen in that feed forward. So that's the first step. And then the second step is to train the probability of the pairs being chosen, of the operators being chosen. So initially we give them some probability of being chosen for each group. And in this step 2, we update those probability being chosen by calculating the loss function for different architectures, and then increase the probability of being chosen for the architecture that gives lower loss function. So this actually very similar to the proxyless NAS, for you who are familiar with it. So we train the weights, and also we train the probability of the operator being chosen at the same time. So we apply this algorithm to 10 test cases, from plasma physics, because I work in plasma physics, to astrophysics, to earth science, and to atmospheric physics as well. This is the GCM. And the inputs are ranging from 3 to 14 scalar values. And the output can be scalars, can be one-dimensional signal, can be 2D or image, with various sizes. And the number of data sets is also varies. So for relatively cheaper simulation, we can generate 14,000 data sets, and we generate 14,000 test data set. But for the more expensive simulations, for example, MOPS, this is the biogeochemistry simulation. And the GCM simulation, which is very expensive, we can only generate around hundreds, or GCM, we can only generate 39 simulations. That's because limited of the time and resources. And from this total data set, we split 50% for training, 28, sorry, it should be 28% for validation. Sorry, 21% for validation and 28% for test. So this is right, yeah. So we use the neural architecture search and train it. And this is the results for simulation with 0D output for scalar output. We can see the R square is 999, has 999 digit here, which is really good. And all the pictures that you see here in this presentation is taken from the test data set, which never been used during the training at all. So we could speed up the simulation from 30 seconds to 2 milliseconds. This is not amazing, but still we can achieve some speed up with very high accuracy. And this is also an example out for emulator for 1D simulation, for 1D output. You can see the orange line is the output from the emulator and the blue line is the output from the simulation. And we could speed up the simulation from 20 minutes to 5 milliseconds, and it generates like 200 outputs. And this is the most expensive simulation that we've been working on, the parameterized global climate model, which takes 3 input parameters and outputs 12 images of the atmospheric opacity. So we could see the difference here is very small. The emulator could produce the very similar image from the simulations, and we could reduce from 1,000 CPU hours to only hundreds of milliseconds in using GPU with very high accuracy. So this is the results for all simulations that we've tested, and you can see the full output in our paper on arXiv. And also we test the accuracy of our emulators and compare it with some non-deep learning models using scikit-learn, and we can achieve up to like 14 times improvement over the loss functions. And in all the case here, we can achieve the best loss function, the lowest loss function for all the tested case and the tested model here. And for you who might be interested in GCM, because in the GCM, we only have like 39 data set, and overfitting is the model is very prone to overfitting. So this is the training loss, validation loss, and test loss for our method and for other methods. And you can see here the SVR, new SVR, linear SVR, they all have very different validation loss and test loss, which shows that they are overfit. And the overfitting is very bad, especially on the last 3 methods. But for our methods, we can achieve a very similar validation loss and test loss. The training loss is a bit lower than the validation and test loss, but we can see the validation and training is very similar, which means that our technique doesn't really overfit as bad as the other techniques. And besides giving the predictions, you could also use the architecture, the final architectures, to give you prediction uncertainty. So this is an example of our prediction uncertainty. So you can see you can sample the architectures randomly and then feed it with the simulation input. And then from that output, you can calculate the mean prediction and the standard deviation of the predictions. And this is the example of the output sampled by our emulator. And it shows which region they are uncertain and which region they are very certain. So for example, on the right-hand side here, you can see that they are very certain on this region, but on the peak here, they are quite uncertain. So you can see which region they are uncertain and how much they are uncertain. So it gives you some prediction uncertainty as well. And also, we also applied this emulator to solve inverse problem for us. So the setting of the problem is we have some physical parameters where we can simulate it to produce observables, some uncertainties, but in inverse problem settings, what we have is the observables, and we want to retrieve the physical parameters. So for example, you see the sun is like yellow, but you want to know what is actually inside the sun. What is the composition of the sun? That's the inverse problem. You have some observations, and you want to retrieve the parameters behind the system, but with the help of the simulations. So the way that we did it is usually by integrating Markov chain Monte Carlo algorithm with our simulations, but that could take a very long time because Markov chain Monte Carlo usually requires like hundreds of thousands simulations. So in this case, we replaced the simulation with emulator and then integrated with MCMC algorithms. And we explore all the uncertainty region. And this is the results. So you can see here, so our observation is the dashed black line. This is a spectrum from one experiment, and we want to know the parameters that produce a spectrum within the blue dash here, within the blue region here. So on the left-hand side, you can see the parameters collected by the emulators and simulation from the Markov chain Monte Carlo algorithms. So you can see the blue histogram is collected using simulations, and the orange histogram is collected by the emulators. So you can see the histograms are very similar here. There are some slight difference, but it's not significantly meaningful. And also you can see the scatter plot, which is very similar. The catch here is to produce this blue scatter plot and blue histogram, it took us 3 weeks. And to produce this orange scatter plot and orange histogram, it took us just under 1 minute. And it was even faster to generate the data set, train the emulator, and then perform the Markov chain Monte Carlo rather than running simulation with MCMC from the beginning. Because the total training from the generating data set, training and then generating the orange histogram here, it only took us around three days instead of 3 weeks. So in conclusions, we have trained deep emulator network search on 10 simulation test cases, and it works very well. And the accuracy improvement is quite high over the other machine learning techniques, and it can also provide uncertainty. It can also provide some prediction uncertainty, and it works well even with limited training data. So some limitation is it doesn't seem to work well in regions of high variability, and for now it only works for simulations with scalar inputs. So thank you.
Thank you so much for a great talk.
Thank you.
We've got a lot of questions coming in here in the chat, and we've got a solid 6 minutes now to take a few of them. So thank you. I'm going to start off with a question from Lauren Kuntz. because she's summarizing a complaint that she's heard from a number of climate scientists who are skeptical about how machine learning will fit into their models.
Okay.
So she asks, how can you tell if your model will behave well on data outside of the training distribution? And the common test case here is if, for example, you train on the current climate and that climate shifts.
So the way that we generate the test data set is by defining some lower bound and upper bound of your parameters, and you could take a very broad range and take the log scale of that parameters, and then just sample from that, just sample the data from that. So as long as it's inside the bounding box, it performs relatively well. But once it's outside the bounding box, the performance starts to degrade. So it's like, it's like just the other machine learning techniques. It's very good for interpolation, but it's not really good for extrapolation.
Mm-hmm. Which makes it good for things like uncertainty quantification tasks, where you can bound your space of interest with original simulations, right?
Yes. So that was the initial motivation for this work, to solve inverse problem quickly.
Yep. And we've got a related question from Anselmo Garcia Cantu, who's asking specifically if you know what happens if you train a global circulation model data on low RCP scenarios and then test on higher ones.
What do you mean CP scenario?
So in that case, RCP scenarios would be the carbon pathways, so the amounts of emissions that you have. So for example, if you train on, go ahead.
Yeah, sorry, I'm not really. So I'm not a climate scientist myself. I am a philosopher-physicist. But sorry, I don't know how to answer that question. But maybe I can answer some question related to the machine learning or emulator.
Sure, I'll throw you in the deep end of architectures. We've got a question from Vivek Mishra asking, for your deep neural architecture search, how were the set of convolutional operators curated? And is there a reason to pick 3D, 5D, and 7D convolutional operators?
Okay, so that's a good question. So this is basically just like trial and error, purely trial and error. So the way that I choose the odd numbered convolutional layer is because it preserves the symmetry. Because and if, for example, if I take 3 convolutional layer, I can drop 1 pixel on the left and 1 pixel on the right. So if I pick like 2 pixels, if I pick the 2 convolution layer, the symmetry is not really preserved anymore, because I have to drop 1 pixel on the right and 0 pixel on the left. So there is no reason. I mean, there's no specific reasons why I choose the odd convolution layer here. And yeah, basically it's just like a trial and error. And this is like the best combination that we have found. So the way that I search this is I perform trial and error for one of the test case. And once I found it, I optimized the hyperparameters for that specific test case, and then just applied the same hyperparameters, the same architecture, super architecture, the same algorithm for the rest of the test case. So this is like the best super architecture for that specific case, but it performs really well for others as well.
Sounds great. And then I'm going to have one more question. Sookyung, an upcoming speaker, you had a question. Would you like to ask it in the chat?
Basically, hello. So I have a question. So usually on supervised learning based physics emulator suffered from the limited number of training data, right? So is it's practically impossible to capture all the difficult physical phenomena from the training data because training data is limited. So I assume that implementing some physics-inspired model design, like such as weird function and so on, is important. So do you have any thought about that?
So it would be like very specific. I mean, for physics, physics-informed deep neural network, it would be. I mean, it would be. We could work for if we know what's the physics behind that. So the idea of this work is to create one set of emulator that we could use as a starting point to build the specific emulator for some specific simulations. So this is still like a black box. So I can't really comment on like a gray box or physics informed emulator.
All right, thank you.
Yeah.
It sounds like that leaves space for a lot of future work.
Yeah.
All right, so thank you very much for your presentation. We're going to
Thank you.
move on next to our second breakout room. There will be
And
chances.
Kelly, if I may add a point before that, sorry to interrupt you. So if this was a great talk by Mohammed, and we have more talks like this lined up tomorrow on the cross-cutting day. And I will post a link in the chat. You can go ahead and register for that, especially a talk by Zico Coulter from Carnegie Mellon. And yeah, we look forward to hosting you in tomorrow as well, where we talk about incorporating physics into deep learning models with implicit layers, like a gray box kind of setup. Thank you.
Thank you.
Thank you.
All right. So for the breakout sessions, some of you might have been here for the first one, but we're going to sort you into rooms of about 10 people each, so that you can have the equivalent of a casual lunch chat with some of the other attendees at this conference. We'll send you broadcast messages into the rooms with questions that you can discuss as icebreakers and warnings for when you come back. We'll resume in the main session here with our next set of talks, which will be updates from people working on using physical emulators for climate science problems at 10 past the hour. So that's 10 past whichever hour you're in most time zones. Okay, so next up, we're going to have a talk by Sookyung, who is a machine learning researcher in the Center for Applied Scientific Computing at Lawrence Livermore National Laboratory. She has a master's from Columbia and a PhD from Georgia Tech, and is now pursuing research projects on deep learning for physical science, including both material and climate science. Sue, are you ready to present?
Yep. So nice to meet you, everybody, and I can see some familiar names from the list. So nice to meet you again. So I'll talk about my recent work on hurricane tracking. The title of this talk is "Learning to Focus and Track Extreme Climate Event," and this work has been done with a collaboration together with KAIST in South Korea and Google. One of the authors is a Google researcher. Okay, so I would like to briefly explain why this hurricane tracking problem or like other extreme climate event tracking problem is challenging, and why is it different with a visual object tracking problem. First of all, there is a butterfly effect in climate event tracking, which means that when you try to track, for example, cat in video, there is no long-term or wider range interaction between each pixel, which means that when we want to track the cat, we don't have to worry about some object which is far from the target object, which is cat. But climate event is not like that. Even if we want to track some hurricane in America, that hurricane event is actually have the correlation with some long-range event like some hurricane in Asia, for example. So those long-term and wider range spatial temporal dynamics should be considered when we design the model. And secondly, no rigid boundary. What that means is when we track the cat in video, for example, there is a clear boundary between background and tracking object. However, hurricane or other climate event is more like a spatio-temporal bluer pattern. So if we just look at the one snapshot of the climate data, there is a possibility that we cannot actually detect or recognize the event because there is a no rigid boundary. So we have to consider these two property of the climate event when we design the model. So how can we tackle those two challenges? To tackle the spatial-temporal dynamic, I decided to use the convolutional LSTM. And in order to tackle the non-blur object, I used this masking type of the trick. So I will explain about this focused learning module and tracking module. So basically, our model is divided by this twofold focused learning module and tracking module. So in focused learning module, we give the model the ground truth of the initial location of the hurricane. So given the hurricane video, the model should know what is the initial location of the hurricane in first snapshot of the video. So let's say this is the first snapshot of the climate video, and we want to track this target hurricane. We just masking out the other part in images. So the input of this focused learning module is masked image of the initial time frame, and the output is the same mask that we used for the input. And then we learn this focused learning module using convolutional LSTM and extract the hidden state from this focused learning module. So we can think like this is like auto-encoder learning the where to focus and what to focus in initial time frame of whole hurricane video. So from that hidden state, we have the information of the target hurricane that we would like to track in initial time frame. And the last model is like a tracking module, which is just a many-to-many convolutional LSTM. We put the input of time series the hurricane imaging, which is like hurricane video, and the output is the heat map of the target hurricane. And we put bounding box regressor, which is just a CNN plus fleet connected layer to extract the exact bounding box information, such as width and height and central information of the center of the hurricane. That's it. And then the losses applied from here and here. For training heat map, we use the pixel-wise MSE, and to learn the run the exact bounding box information, we used L2 loss between ground truth and this predicted bounding box. And our model is fully trained by end-to-end fashion. Okay, this is the data set which the climate scientists may be interested about. We used modeled output, which is Chem5 data set, mainly because we do not have enough labeled data using reanalysis data. So we decided to use Chem5 data, which have a lot of labeled hurricane data. And we used 3 different channels. So when I say hurricane video is not actually multimedia video, obviously, each channel is not RGB, each channel is the climate variable, such as surface level pressure, zonal wind, and meridional wind. And those 3 channels is hand collected using sensitivity test. We tried a different combination of the channel and picked whatever the best. And then to label the hurricane, we used TICA software, which is developed by the Lawrence Berkeley National Lab. When we learn the TICA from the input data, what we can get is the exact latitude and longitude information of the hurricane center and diameter of the hurricane force wind, which is used as like a radius of the hurricane. And then we used a 20-year-long record from 1996 to 2015. And the resolution of the Chem5 data is basically 0.25 degree. But to make this data fit into the memory of our computer, we upscale the data as 0.5 degrees. So resolution is about 55.5 kilometer. Okay, this is basically one of the best result. Each time step is 3 hours. So I'm showing you the test case of time length of 110, which is corresponding to 330 hours, which is pretty long time. And model just to know what is the ground truth center information at initial time frame. So this is the input images, which is like climate images. And this white is the ground truth hurricane bounding box, and blue is our prediction. And we can see that ground truth matched with the prediction bounding box pretty well. And at time step 80, we can see that the new hurricane is emerging on the right side and slowly approaching to our target hurricane. Even if there is a new hurricane event, our model is not this strict at all, and stably and rigorously track the only target hurricane until the end. And we compared our method with state-of-the-art visual object tracking method, which is solving exactly same problem, given the initial state, initial time frames, target object information, and let the model track the rest of the object tracking in the video. So we compared RT MDNet, MDNet, EcoDeep, and SIMFC. Those four are popular visual object tracking model, and our model outperformed all four of them in terms of success rate and precision. And the climate AI, as you all know, suffers from the lack of labeled data issue. So to tackle these challenges, we use the data augmentation technique, which is generate the fake hurricane labeled data and dump them inside of our training set and use it when we train the model. So to make the fake hurricane labeled data, we basically use the conditional GAN. So first, we generate the trajectory using social GAN. Social GAN is the model to fake the trajectory of the pedestrian movement. So basically, inspired from that model, we synthesize the fake hurricane trajectory and take each coordinate value of the hurricane center. And then from that coordinate, we synthesize the heat map of the hurricane. And from this image generation stage, we just use the conditional GAN, which is inputting the heat map of the hurricane and synthesize the image of the hurricane. And we can concatenate them together and use that as the hurricane video, fake labeled hurricane video. After a few years from this paper published, some state-of-the-art video synthesized technique has been come out, like a pics-to-pics or everybody's dance now. And that would be the future work to use that model to synthesize the hurricane video. So this is basically how the fake hurricane image looks like. This upper low is the real hurricane image, which is showing the low surface level pressure around the center and the spirally rotating wind direction around the center. And our fake hurricane image is a little bit low quality than ground truth because this is very blue, but key property of the hurricane image is well mimicked, such as low surface pressure and spirally rotating wind pattern. And interestingly, if we add a little bit of the augmented data, the accuracy jumped, the success rate and precision jumped a lot compared with the case without data augmentation. So that was a good sign. And I will show the demo of our model. So this is the case without data augmentation, and white is ground truth and green is prediction. And we are tracking until the end of the hurricane. And this is the case with augmented data. And we can see that green is following white bounding box pretty well. Yep, so this is the demo of our work. So, okay, to sum up, we designed the model to tackle challenging hurricane tracking problem using focus and tracking model using convolutional STM. And we saw that data augmentation using conditional gain actually help a lot to enhance the performance of our model. Yep, thank you.
Thank you, Sue, for the great talk here. We've just run a couple of minutes over, so I might have to push the questions to the chat on this one. I can see that you've got a couple coming in with people especially interested in the data sets that you're using for this training.
Okay.
But for the main chat here, I'd like to move on and introduce our next speaker, Valentina Zantedeschi, who is a machine learning researcher with a PhD from the universities of Saint-Étienne and Lyon. She works on form kernel methods and learning theory with adversarial examples in decentralized learning, as well as object recognition and disease detection. Valentina, are you here? Okay, Valentina, are you muted? Yes.
I think Valentina needs to be given co-host privileges. All good.
One second. There we go. Valentina, can you speak now? Great. I can't hear anything yet. If you're speaking,
okay.
You might be.
Can you hear me now? Yes.
Yep, there you go.
Perfect, sorry. So thank you for giving this opportunity of representing our dataset. So here is really a presentation about presenting this dataset that we built for performing cloud classification with machine learning. This is a result of a collaboration between machine learning experts and climate science specialists. So I would like to start by giving some motivation about why it's important to being able to perform cloud classification at the global scale. Because when we look at the current projection for climate, there are a lot of uncertainties. These uncertainties are due mostly because the physical global, the climate models that we have don't capture all the processes that happen at small scales, including these, like the cloud formation and cloud feedback with the Earth system. And this actually have a huge impact on the Earth system, and so causes a lot of uncertainty for the future. For instance, here, when we look at the global warming, we see that actually the projection of the temperatures are quite uncertain. So in order to reduce the uncertainty, it would be necessary to first key steps. The first one would be really to be able to identify the type of clouds that occurs over the globe in the atmosphere, because each type of cloud interacts with the system, the Earth system, in a different way, depending on their composition or their thickness, etc. After that, once we are able to identify the type of clouds present in the atmosphere, of course, it will be interesting, like, and necessary to study how they change over time and space, how they interact with the environment, and etc. And the first of these steps can be tackled with machine learning. And this is why we are releasing this dataset, because we are hoping that the machine learning community start to work on this problem. So we built our dataset by merging two open source datasets that collect satellite images. The first one is this NASA Modi's Aqua product, which gives us global coverage for this full view of the Earth day by day for several years. And this is at a high spatial resolution. So for each given location on the Earth. We have selected 13 different raw radiances that fully describe the clouds present on the Earth. You can see, for instance, an example here of the visible channel that I plotted in the right of the slide. But also we have other 9 computed channels, which are computed from the raw radiances, extracted from them, and give direct information about the cloud properties, such as their thickness, the temperature beneath them, etc. And also we have this cloud mask, which says for each pixel on the globe, if that pixel is certainly cloudy or not. So along with this first, this set of images, we also have some labels that we extracted from a second data set, which is the CloudSat product, also by NASA, which give us more accurate information than the first data set, because it uses only, it uses also some active instruments like the radar and LIDAR. And so it gives us really more information about the clouds, especially in the labels. One of these 8 cloud categories, main categories that are well studied and that you can see here. We can distinguish these clouds based on their altitudes or their thickness or their precipitation intensity. And so we have this information not only in a 2D, like for the other dataset, we also have it vertically. So we can distinguish these actually instruments can distinguish if there are different type of clouds and different number of layers of clouds in the same pixel. The problem with this is that we don't have this information for all the pixels for the entire globe. We only have them for along the track of the satellites that were collecting them, because the PW is extremely short. So here is really about extending this supervision to the entire globe using the features that we have from the other source, from the Modus Aqua. So from a machine learning perspective, the dataset gives a lot of challenges. As I said, the supervision that we have is really limited, so only a few pixels for the entire globe. But also, as we have this resolution, vertical resolution for the labels, we happen to have multiple labels for us in a single pixel, and also because of the alignment that we applied for the 2 sources of data. This is the case because of that as well. But also certain type of clouds are more common than others. For instance, the thin cirrus clouds are more common than the deep convection ones. So we have a problem of class imbalance as well. And not all the channels are available for the entire day. Some of them are available only at daytime, like the visible channels that I showed you before. And finally, it's not true that only 8 types of clouds exist. It is well known that there are many of them. You can consider there are subtypes among the major categories, 8 categories for which we have the annotations. So there's a second problem of finding new clouds, new type of clouds, and being able to validate these newly found clouds. So in our paper, where we presented the dataset, we also provided baseless performance analysis performed on 3x3 tiles of pixels. So these are some updated results for the entire year of 2008. So we trained this hybrid invertible residual network on a subsample of the tiles sampled all over the globe, both labeled and unlabeled in a semi-supervised way. And you can see here, for instance, the classification for a day of 2008. you can see that even if we didn't force it, there is some spatial coherence between the classes that we learned, which is great. But also here in the table, you can see the other metrics, machine learning metrics, to assess the quality of the predictions. So we use a test set from the tiles, label tiles that we had. And you can see it's with a pretty good job. There's still some room of improvement. So this is just a baseline that we provided. But of course, here we are trying to solve a physical problem. So we would like also the model, the classification model that we have to have physical meaning. Also because the supervision that we have is so limited that it's hard to say if, and it could happen also that there are some noise in the labels. It would be better to have other metrics that would tell us if the model is physically meaningful or not. This is why we proposed also some other metrics based on known cloud properties. For instance, here you see these metrics for the deep convection type of clouds. First of all, we compare the distributions of the physical properties of the clouds between the true label one, the distribution of the true labels, and the one of the predicted classes. Here you can see the ARISNet predictions. And you can compare them visually. For instance, here you see that for the liquid water path, for the deep convection, there are two modes that are somehow captured by our model, the ARISNet model. But of course, also quantitatively, you can imagine to use some divergence measure between the two distributions like the KL. We also propose to study the cloud occurrences, which are like saliency map average over the year, like the probability of a class occurring at a certain location on the globe. And we compare these found cloud occurrences with the one with other found in other studies in climate science papers, and check if it makes sense that a cloud occur in a certain region of the globe or not. We can imagine also to have to start to also use some spatial entropy to see if the classification is good or not. So the dataset is now available. It is available for the year 2008, and soon 2009 and 2016 will come soon as well. So you can follow the link here to access it and download it. You'll find also some more information about the dataset and how to download it and read the files. If you have any feedback or questions, we will be happy to take them, and thank you for your attention.
Kelly, it seems like we can't actually hear you.
Thank you. Valentina, I was thanking you for a great talk and for speaking about something that I know interests a number of our participants, judging from our questions early on. I'm going to push questions for this talk into the chat because we're running a little bit over time. In the main session here, we're going to take a 1-minute break so that we can switch over our virtual setup here. And then we're going to have a keynote talk from Lester McKay at Microsoft Research, which will be introduced by Pitak. Thank you.